Okay, so this is chapter 4. This is my favorite chapter, I'll be honest. It's got the most, it really starts to dive down into the forms of energy, the physics of energy. So I might move kind of quickly here. It's only because I'm excited and like this chapter a lot. Sorry, I apologize ahead of time. You'll also note, I've got a few notes from previous years. This was lecture 7. This is actually something that Mark Olson put together. I'm not going to hold you to much of this, but I am going to use his little equation here as an inspiration for something we'll do in class. So he's looking at kinetic energy. You can also see he's got that power is energy per time. You're going to see that time and time again. Here is his potential energy. We can go over that a little bit for sure. Again, I am not going to hold you to these notes. I'm just kind of scrolling through what Mark had from last time. Heat, light, motion. There's the heat equation. Perfect. We can do that one too. Electrical. There we go. Yeah. Combustion, chemical. Nice. Okay. So Mark's actually pulled a lot of different things together, and that was from this past spring, yeah, February.
Yep, I have those notes.
You got them?
Mm-hmm.
Nice. Okay, so chapter 4, forms of energy. One thing I want to write out right away is that energy is measured in joules and has the same dimensions and units as work. So energy and work have the same units or dimensions. Typically, what one means by work is that when you use energy to do something useful. So if you push a chair across the floor, you're going to be using some of your body's energy to do work. But they're both measured in joules.
What's that symbol that has dimensions of?
And ampersand, sorry, it's a.
And units?
Yeah. Ampersand. Okay, so same dimensions and units as work. Now, what do I mean by dimensions versus what do I mean by units? So obviously we know that we can measure energy in joules, and that is a unit. Give me an example of some dimensions that you know.
5 by 6.
Dimensions. Okay, 5 by 6 what?
Feet.
Okay. Are feet a dimension or a unit? A unit of what?
Measurements.
What type of measurement?
Inches. Linear.
Give me something else. Yeah, it's linear, but what are you measuring when you measure something in feet or inches or in a linear manner? What are you measuring? Distance. You're measuring distance. You're measuring space itself. Okay, give me another. Time. Yeah. So here's length. Todd just mentioned time. What's a unit of time? Seconds, hours, whatever. Unit.
Okay, so what do you mean by dimensions?
Of time. Well, so could I measure time in inches? Why not? They're different dimensions. Time and space are different dimensions. That's what I mean by dimensions.
So time, space.
Keep going.
I stole those two from you.
Well, tell me something else. Area is distance squared. Give me something else that you might measure in the morning in the bathroom that you would not express in either feet or seconds.
I don't want to answer.
Volume.
Volume is also space. Keep going. Volume is also distance.
Angle.
Maybe at the doctor's office. Angle, yeah, I'll put radians down, sure. I'll put degrees, degrees or radians are units of angle. Degrees and radians actually don't have any dimension. It's an angle. It doesn't have a length.
Isn't there 4 dimensions?
You might say there are 4 dimensions, 3 length and 1 time. But keep going though. That's the special theory of relativity. When Einstein introduced the general theory of relativity, he had to add something else to his equations rather than just length and time. I think it's something you probably get measured when you go to the doctor's office.
Temperature?
Weight.
Yeah, it's your weight, it's your mass.
Mass?
So there you go. So with these 3 dimensions, length, mass, and time, and we'll call this, the kilogram, the lb, units of mass. So with these 3 dimensions, mass, length, and time, we can derive several other dimensions. Energy itself, I'm going to call a dimension. You wouldn't measure energy in inches or measure energy in pounds or measure energy in seconds. You have to measure energy in joules. So we're going to take mass, length, and time, put them together in a special way, and come up with the joule. That's our first order of business. Okay, so let's do it this way. We'll start with Newton's second law. Second law. He stole the first and third from Galileo. The first one is that objects in motion stay in motion, and the third one is that forces are equal and opposite. This one, though, is really his, and it just says that force equals mass times acceleration. Hey, we'll see you next time, Rain.
Yes.
So, this is sort of the algebraic way of writing it. Now I'm going to write it in dimensional form. So, and I'm just going to use the 3 dimensions that I mentioned previously, mass, length, and time. And for mass, I'm just going to use the big M for units of mass. Could be kilograms, could be pounds, it doesn't matter. How do we express acceleration typically?
Time, multiplied by, or no?
Remember what the acceleration constant is? Ish. Gravity, all that stuff. 9.81 meters per second squared, 32.2 feet per second squared. So acceleration is always measured in length per time squared. That's force. And right here, and force is measured in newtons. And we can convert newtons to pounds, but newtons are the SI unit of force. Now, I know that work equals force times distance. So for example, very simple example, if I've got a surface here and I've got some mass sitting on it, I'm gonna push that mass like so, And if I had a little miniature scale between my finger and this mouse, I could measure how much force I'm using, a few ounces, a few millinewtons, what have you. And then I push that a certain distance. So I multiply the force times the distance that gives me the work. Same exact formula goes into calculating miles per gallon in a car, right? Because the car is pushing against the road, it's gone some distance, you look in the gas tank in the end, there's that much gasoline missing, that's how much energy you used to do the work of pushing the car down the road. Same thing for airplanes, same thing for any mode of travel. So that's work. Force times distance. Now, I know that force has units of mass times length divided by time squared. Distance just has units of length. So now if I come over here, I'll write out mass times length over time squared times length. Right, so this chunk up here was my force. This chunk up here is my distance. Combine them together, I get mass times length squared over time squared. Those are the dimensions of energy. If you do it some other way and get some other weird dimensions, it's wrong. More specifically, these are the mechanical dimensions of energy. Later we can get into the electrical dimensions, but ultimately they come back and always look this way. Energy is mass times length squared over time squared. Okay. Now, looking at the book, and this is fundamental to everything else we're going to cover in this chapter. Okay, so 4.1, what the authors lay out is they're looking at electricity. I just mentioned mechanical. Mechanical can be kinetic. It can also be potential. There's heat. We'll look at heat also. There's light. There's nuclear. There are many different forms. But when it comes right back down to it, they're all ultimately going to have this type of dimension. Okay. So let's do a little problem. And let's take a look and say we're over at the Mobash skate park. And what I'm going to try to do is use physics to determine how quickly someone in this little skate park would be going at the bottom of the bowl. So here you are up on the skateboard, and what we're going to do first of all is just do this mechanical energy experiment. So I'll write it this way: energy potential equals the mass of the item, in this case the skater, times the height times the gravity. Now hopefully you can just look at this by inspection and see that, okay, I know that energy is always measured in dimensions of mass times length squared divided by time squared. Well, right there's your mass. Right there is basically your acceleration, length divided by time squared, and there's your height, which is also length. So with that, I've just confirmed that this equation, energy potential, or potential energy equals mass times height times gravity, is dimensionally correct. Okay, now, what is the, before we get too much further, I'm going to write out the kinetic energy formula. So E kinetic equals 1/2 mv squared. So again, I look at that, and I'm like, okay, it looks like I'm in good shape. There's mass with dimensions of mass. Here's velocity, which is always length per time, miles per hour, meters per second, what have you. So again, I've confirmed that I've got length squared over time squared. So these two forms of energy, potential and kinetic, both have the proper dimensions. And now we know that we can actually exchange them mathematically, just as this skater's about to do physically. Question? Good, okay. So what happens is he's going to come down into the bowl and have some velocity as he's down there. The question is, we want to know what that velocity is. So first law of thermodynamics tells us that we cannot create or destroy energy. And so all we need to do now is figure out how much energy he started with, and then how much he's got at the bottom. Knowing those two numbers are the same, solve for velocity, and there we have it. So this type of analysis gets used a lot of times in engineering forensics too. I was just at the National Society of Professional Engineers in Seattle, and there was a case where a woman had been hit by an automobile, and the police had stated that she was standing on a particular corner just a few feet from where her body was found. The automobile that hit her was going at a speed substantial to indicate that her body probably flew a much further distance than what the police report said. As it turned out, rather than the woman sort of being an innocent bystander on the sidewalk, close to where she was found, she was actually in the middle of the roadway and got hurled through the air 60 or 80 feet. So the same little analysis that we're doing for the skateboard park does have bigger implications for engineering forensics. Same thing, like, oh no, officer, I was only going 20. Well, why do you have skid marks that are a quarter mile long? I don't think someone going 20 is going to have skid marks. So this type of analysis gets used all the time in this type of work. We're not just having fun at the skate park. So what we're going to do is just write out E kinetic equals E potential. Start out as simply as possible. Now we can just start to add in our variables. So the kinetic energy is 1/2 mv squared. The potential energy is mgh. Now we know that we're trying to solve for velocity, and rather than, and this is also something that's very important for the rest of your energy technology career. Up to now, we've been doing a lot of problems, just like the word problem that we just did on the board with Tim, and we just kind of kicked through the numbers. I haven't written any numbers down yet, except for the number 2 under the 1/2. I'm just doing algebra. So what I'm trying to emphasize here is that it's important that you solve the algebra first and save yourself a lot of the grief of making arithmetic errors. I know I'm prone to them. In a lot of ways, it's easier to make an arithmetic error than it is an algebra error. So I'm just going to keep this as simple as possible as I can for as long as possible, and then come in and do the arithmetic. Is that clear in terms of the steps, in terms of solving the problem? Okay, so the next thing I'm going to do, I'm going to see that mass is on both sides and just get rid of it. So I've got 1/2 v squared equals gh. And this is a pretty big breakthrough. And this is a problem or a misconception that every single person on this planet had until Galileo came along in 14 whatever and said, no, the mass does not matter. We just took it out of there. It really doesn't matter how heavy that person is. It will not affect the velocity. Will it in practical terms? Yeah, because there's some wind friction. If this person's wearing a parachute, obviously they'd be going slower. If they were in a little bullet-shaped car, they'd be going faster. But for the first order approximation with no friction and, the guy doesn't wipe out on the way down, the mass doesn't matter. It's irrelevant to the problem. Okay, so our next step is to say v squared equals 2gh, and then finally the velocity equals the square root of 2gh. So you might say, well, gosh, what numbers do I put in there? Well, we can just kind of assume that it's a 6-foot bowl, so the height can equal 2 meters, top to bottom, and we know that gravity is approximately 10 meters per second squared. So from there, and again, the skateboarder is just at a dead stop. His initial velocity is 0. So this equals the square root of 2 times 10 times 2 equals the square root of 40. I think I've got that on my calculator down here. 40. Where'd that square root button go?
6.3.
There we go. I just used that little root y. 6.3 meters per second. And that's somewhere around 12 miles per hour, which seems reasonable. You can see someone going about 12 miles per hour in a skate park. Yes?
10 and the 2, did that just come off of something you measured?
Oh, you know what? That's a great question. Let me reiterate that. Good question. Let me write that out one more time. V equals the square root. So this 2 was just from the 1/2. This 10 is actually meters per second squared. That's that's gravity. Gravity is 9.8 meters per second squared. I just used 10 instead of 9.8. 10 meters per second squared. And then 2 meters. Yeah, thanks for asking that. Kind of hustle. Yeah, my units disappeared, didn't they? Let's put them back. So equals the square root of 40 meters squared per second squared equals 6.3 meters per second. Is that?
The second 2 came from height of the ramp.
Oh, okay.
Yeah. That 2 was from the algebra, that 10 was from the gravity, and that 2 was h. And I just neglected in my first little round to include the units. But thanks for asking me. Yeah. So that's in fact, you should make a habit of doing that so that you don't lose your units. All right. So that's a little nice little example from 4.1 more or less.
So if you had your height of your ramp in feet, you would have to convert it to meters.
Yeah.
Because of your gravity is in meters per second.
Absolutely, yeah, and that's another really good point, is that just as we did in our solar thermal problem here, we had to convert from inches to, square inches to square meters. If for whatever reason you were given your measurements in different units, then, yeah, you need to do the units conversion first. That's why there's, the contention about using conventional versus metric units all the time. You got to pick one or the other. All right, I'll take a little pause there.